to record this, sorry. In a large number of trials, we can expect to get a 1. So in this case, large number of trials might be a large number of dice rolls. We can expect to get a 1 about 1/6 of the time. How often? So it's really how often something will occur in a large number of trials. All right, now, from that, we also had some probability rules, some of which are even on your formula sheet, okay? So the complement rule is not, but if I want to know what is the probability that A does not occur, I do 1 minus the probability that A does occur, okay? You guys already know this. If I say if I tell you that the probability that Miss Meister needs to refill her coffee mug is 95%, what's the probability I don't need to refill my mug? 5%. Like, it makes sense to just subtract from 100%, yeah? Okay. The other thing about probabilities is probabilities have to be smaller than 1. Okay? And because of that, little side note, a p-value is a probability. P-values have to be smaller than 1. Less than or equal to 1. Technically, you could get a p-value of 1. Okay. Multiplication rule sets the probability that 2 events occur is equal to the probability of A times the probability of B, given that A has occurred. By the way, guys, this is how tree diagrams work. We multiply probabilities, right? Across a tree diagram, that's what it is. Okay. Now, the following 2 probability rules are on your formula sheet, and one possible, as you're trying to choose which strategy you're using for a probability question, one of the things you could do is use these next 2 rules that are on your formula sheet, okay? The addition rule is that the probability of A or B is the probability of A plus the probability of B. Felix, would you mind shutting the door while you're up? Thanks, bud. Does this look familiar? Okay. Also, the one that I envision you guys using more frequently, the probability of A given B, is equal to the probability of A and B over the probability of B. What do you guys think so far? All right. All right, two-way tables. Do I need to explain to you what a two-way table is? Okay. On a scale of 1 to 5, how comfortable are you guys finding probabilities from a two-way table? If I give you a two-way table, can you find the probabilities I ask you to find? Okay.
I'm not 100% like if you did it, I'd be like, probably like, oh yeah, I can do it. Oh yeah.
Okay, so let's make up a two-way table really quick. But please, please, please recognize that I'm making this up really quick, and the amount of creativity going into this two-way table is going to be very, very bad. Okay? All right, so let's go ahead and I don't want to do this one. The reason I'm not doing left-handed and right-handed, y'all, is one of the free response questions that we're going to do later is also left-handed, right-handed, and it's going to feel really silly. So why don't we do, underclassmen versus upperclassmen, job, no job. And let's go ahead and say this will be the total and total. And let's go ahead and say this is 1547, which makes this 62. And then we'll do 41, 12, and 53 for a total of 115 people. And then let's be 6. And those numbers work out fairly nicely. Everybody good? Okay. So if I gave you this and I said, what is the probability somebody is an upperclassman? Could we find that probability? Yeah. What is it? 53 out of 115. And then chances are, if you're given a two-way table, you're going to try to compare those things. So we might write that as a decimal, but I'm not stressing about it right now. Okay. All right. What is the probability somebody has a job? 56 out of 115. Cool. And what is the probability somebody has a job given that they are upperclassmen? 41 out of what?
Oh, 41 out of 53.
41 out of 53. Now, so AP exam's coming, you know we're finding a given probability. This is when we might go back up to this formula to help us see that, right? So we would do job and upperclassmen, which is the 41, over just given upperclassmen, so upperclassmen. So that's why it's 41 out of 53. Like this formula can help us. Everybody good? So probabilities from a two-way table, feeling okay? Yeah.
Is that on the formula sheet?
This one?
Yeah.
Yeah. Those two are on the formula sheet. Okay, so for tree diagrams, we will have some opportunities to explore tree diagrams today. Okay, these are really helpful if you are given a conditional probability. Now, that being said, my rule of thumb is if I'm confused about a question, I'm going to try to build a tree diagram. When I get a probability question, I have no idea what to do. Even though tree diagrams are tedious, they do tend to help us understand what's going on fairly well. All right, now. In your calculator, you have that list of distributions menu, and those are probability distributions. So one approach to, you get a problem where they're asking you to find a probability. One approach you can take is to, when you're stuck, you'd be like, oh, I wonder if there's something in that distributions that can help me. In particular, I feel like that's going to help you identify binomial and geometrics, okay? All right. How many of you guys feel comfortable using normal distributions? Like when you know something is normal, I would imagine we feel pretty okay with using normal distributions. Okay, so I'm not going to talk about those. Now, binomial and geometric distributions are a different kind. Both of them are the result of binary trials. So let's keep going with the Meister and the coffee refill. Okay, let's go ahead and say the probability I need a refill on any given day is 95%, which, by the way, is, I think, a low estimate, right? Okay? If that's the case, and then we looked at an entire week, wouldn't we have multiple trials of Miss Meister needs a refill versus not needs a refill? Any one day is binary, and then over time we would count whether or not I needed that, right? Okay? So for a binomial, we have a set number of trials. And x, my variable, equals the number of successes. Geometric, our variable is equal to the number of trials until success. In other words, someday, like if we were to be like, all right, we're going to figure out how many days Meister can go without refilling her coffee, what's the probability she can go 3 or it takes her at least 3 days to need more coffee. So we don't know how many trials. The number of trials is the variable, okay? All right. Now, with binomial and geometrics, you have the PDF function in your calculator, which is going to tell you the probability x is equal to something, okay? CDF is going to tell you the probability x is less than or equal to something. Any other version of it, you have to be clever. So first thing I would do if I get a probability question is I would read it, and for some of them you're going to be like, oh, I know where to look. I'm going to go do this, okay? But then when I don't know what I'm going to do, I might say, hey, can I build a tree diagram? No, that doesn't really make sense. Cool. All right, then I'm going to say, oh, can I use the binomial or geometric stuff in my calculator? Okay? If I still am, like, confused, okay, like, let's say you're given something where you want to find the probability x bar is something, either greater than or less than or whatever, okay? So then you got to look at three things. When are the x bars normal? If n is greater than or equal to 30, right? The mean of the x bars is always the population mean. And the standard deviation of the x bars would be the population standard deviation over the square root of n. And they would give you that stuff in the question, okay? And the very first wrong answer will be just using the regular standard deviation. And likewise, they might give you all the information you need to calculate a p-hat, and the same idea. So then you're going to use the normal distribution, and np greater than or equal to 10, and 1 minus p greater than or equal to 10. And then the mean and the standard deviation, and those formulas are on that formula sheet. Does this feel familiar? I would look at these two formulas on my formula sheet because I have a formula. Is everybody with me? So, all right. We also had things called random variables. So, a random variable is anything that has, they're usually discrete, that has an outcome that's quantitative, okay, and the probability of that outcome. So this was like based on the mulch sale that the boosters does, okay? So let's say for any given customer, those are probably low amounts of bags box. I don't know many people that only need 2 bags of mulch, but, I made it up, okay? All right, and if I asked you guys, here's my number of bags sold and the probability for each one of these, okay? Can we find the mean and the standard deviation? Can I just add 2 plus 3 plus 4 plus 5? And then divide by 4? Because they're not all equally likely. So instead what I add is, so the mean of x in this case would be 2 times 0.2 plus 3 times 0.25 plus 4 times 0.35 plus 5 times 0.2. And you wouldn't be expected to show that workout. But hopefully this feels really familiar. I feel like this is one of the ones where we kind of talked about this quite a bit. So let's go ahead and say that's a 0.4 plus 0.75 plus 1.4 plus 1. I think it is 3.55, but I sure would love it if somebody double checked me on that.
Yes.
Cool. And having a copy of the answer or the formula sheet in front of me, I want to kind of show you guys. Kind of, this is where that formula is. Like the sum of all the possible outcomes times their probability. Okay, so this is technically on the formula sheet. So this is the outcome, this is the probability of that outcome, and then that sigma means you add them all together. The reason I'm pointing this out is I feel like this is a relatively familiar thing. Then when I ask you to do the standard deviation, it gets messy. But I want to point out that the standard deviation is of that kind of that same form. Okay? So if I wanted to use the formula sheet to help me find these, I would do that the standard deviation is equal to the square root of, and it's saying, well, first I'm going to take each data value. So the first one was 2, the second one was 3, 4, and 5. And then I'm going to subtract the mean, which was 3.55. And square that. and then multiply by the probability of that particular one. So the probability of 2 is 0.2, the probability of 3 is 0.25. And then we're going to add all of those up, but that's what that sigma means. So you get the basic premise of what this is supposed to look like. I didn't do a very good job of space here. Let's do this. Now, that being said, I don't anticipate you having to do this, okay? Or at least I don't anticipate you having to do this during the free response section, okay? So if this was on, say, the multiple choice, you could. Let's get this out of the way. Hold on. You could throw these in L1, these in L2, and use your probabilities as a frequency list and run the one variable stats. So if this is on the multiple choice, I would not do this process. I would throw them into my calculator and do the one variable stats using L2 as a frequency list, the probabilities as a frequency list. And in fact, this is a relatively small thing. I'll take you guys through that because I don't want to do that calculation. Okay. You're going to go to stat, edit. Let's go ahead and clear some of this stuff out. So we run those one variable stats the way we've always done, okay? And usually we just leave that frequency list blank. If we don't have any probabilities or list of frequencies, we leave it blank and we just say, but this time because we have a list of frequencies, those are in L2. Oh, that's right. This calculator version doesn't do this. Yours does, though. Yeah? So what did you guys get for your standard deviation? And I'm assuming you got 3.55 for the X bar. And what did you get for the standard deviation, Rishi?
1.023.
1.023. Cool. Yeah, the calculator version of the app, or the phone version of the app doesn't do it. Is everybody okay?
Can you show how to do it again?
Yeah.
I put it all in, but I
Stat, you're going to arrow over to calc. And you're
okay.
and you do those one variable stats. You're just going to put L2 in as your frequency list, and you can get to that L2 by doing second 2. We good? All right. Now, what if I take this probability table, and you know what? if they sell the bags for $4 a bag, how many dollars or what? So 2 bags all of a sudden becomes $8. Is everybody with me? And likewise, 3 is $12. So what we're doing is I'm going to make a new variable C that is equal to 4 times however many bags they sell. Is everybody with me? Okay. And so that's how much they charge for just for the mulch, yeah? And so what is the mean of C going to be? Well, if I multiply each value by 4, isn't the mean going to get multiplied by 4? Is everybody with me? So, 355 times 4, which is really easy to calculate inside your head. Let's see, 350 by 4 is $7, is $14 plus another 20 cents. So I think it's $14.20.
You said $13.20? 14.
I said 14. Yeah, I said 14.20. And then will the standard deviation change here? So, are you guys with me that standard deviation measures how spread out stuff is, which kind of tells us also how much uncertainty we have, okay? How spread apart are the 2 and the 3? They're 1 away from each other, yeah? How far apart are the 8 and the 12? They're 4 away from each other. Did they become more spread out from each other when we multiplied by 4? Do you guys see what I'm saying there? Like the distance here was 1, and then it became 4 when I multiplied the number of bags by 4. They got more spread out by a factor of 4. So will the standard deviation change?
Oh.
Because my variables are more spread out by that exact same factor. Is everybody good? So my standard deviation of the costs is going to equal 4 times that 1.023, which is, an amount. So $4.092, I think. Cool. All right, now, let's go ahead and say that the final price is going to be how much they charge for the mulch along with the $15 delivery fee. Okay? So, if I multiply by 4 and then add 15, that final cost. You guys with me? So all of a sudden that $8 becomes $23, the $12 becomes $27. And you guys, what's the distance between the 23 and the 27? Like, it's still 4, yeah? So adding that $15 didn't make it more spread than if, so my standard deviation of the final cost is going to be $4.09.2. Now, what's going to happen to my mean? If everything gets charged $15 more, the mean's going to go up by $15. So the mean final cost is going to be $29.20. So big idea. When we multiply or divide an entire distribution by the same thing, okay, these are called linear transformations. If I multiply or divide, both the mean and the standard deviation will change. Adding and subtracting, only the mean will change. Everybody good? All right. All right, now consider each Bag of mulch is supposed to have 2 cubic feet, so the mean of the mulch in a bag, so I'm going to call that mu b for one bag, is 2. And the standard deviation of the mulch in one bag is 0.5. Oh, and in this case, we have that they would be normally distributed. Okay? So if I'm getting 4 bags, are all 4 bags going to have the same weight, the same amount of mulch in them? What do you think? No. So I can't just multiply by 4 because multiplying by 4 would assume they're all the same. Okay? So instead, like we're going to draw this picture where I do bag 1 plus bag 2 plus bag 3 plus bag 4. Bag 4 is definitely the worst normal curve I've ever drawn. All right, and if I take 1 from each of these bags, and add them up, what does that new distribution look like? What do you guys think the mean of that is going to look like?
Should it still be 2?
It's not going to be 2.
Oh, no. Shouldn't.
Because I'm just adding the total weight of the bags, right?
Yeah.
And according to your intuition, what should the total weight of those bags be? 8. And guess what? For the mean, you can trust your intuition. Okay? Now, for the standard deviation, I'm going to call this T, do not trust your intuition. Because your intuition is going to want you to say that it's 2, where you do 0.5 plus 0.5 plus 0.5 plus 0.5. And that's not what you're supposed to do. You're supposed to do the square root of 0.5 squared plus 0.5 squared plus 0.5 squared plus 0.5 squared. Which, by the way, is equal to 1. Do you guys remember having to do that weird squarey Pythagorean theorem thing? Okay. All right. So lastly, the question is asking, what's the probability that they get more than 9 pounds of mulch? That would be a really good day.
We just use the CDF.
Now we have a normal distribution. We just use normal CDF. Do you need to use normal CDF? In fact, I bet I know what normal CDF is going to give you. I'll bet you $1,000. Anyone want to take the bet? Does anybody think they can do this without a calculator? Specific rule we learned. You guys, are you guys with me that this is exactly 1 standard deviation? So if we use that 68 rule, this would be 34%, leaving the other half of this to be 0.16. My guess is you guys get 0.162. Or pretty darn close to that.
At 0.158, but close enough.
Same idea. Really, it's the same idea. It's 0.842. I took the 0.02 in the wrong direction, basically. 0.002 in the wrong direction. How are we feeling, okay? Has this been helpful in terms of going over stuff? Okay, so let's take a few. This seems like a really good place to take a break. And then when we get back, the formula